What if mathematics isn't about answers, but about obsessions? What if every problem is really just the beginning of some more dangerous question? And what if the thing that makes mathematics powerful isn't certainty, but restlessness? Today, we're talking about where problems come from, why mathematicians chase extremes, fastness, smallness, tightness, and the most elegant. What if computers and now AI are changing what it even means to understand something? It's a story of people who look at the world or their own ideas and see where it can be pushed further. Welcome to another episode of Breaking Math. I'm your host, Autumn FNAF, and I'm joined by my illustrious co host, Noah John Syracuse. In today's episode, we're joined by Ian Stewart, a mathematician, author, and one of the greatest modern mathematics storytellers. Welcome to Reaching for the Extreme. Now, where do problems come from? We're already seeing that problems don't come from nowhere. And sometimes they come from irritation, curiosity, and from noticing that something doesn't quite sit right. So I'm curious what inspired the book for you?
Well, I think mathematical problems come from the real world, so-called, from the natural world. In the past, enormous important things have happened because somebody looked at a snowflake and thought, why do they look like that? Or threw a pebble in a pond and watched the ripples. And sometimes the other extreme, mathematical ideas come because some mathematician's sitting there not really thinking about anything very much. And so think, now, what about, um, there's a whole bunch of ideas I've been thinking about, and I've just noticed there's a kind of gap in the middle of them all. There's a hole that needs to be filled. There's some obvious questions that ought to be asked, and then that starts them off. And of course, historically, what happens is you get those two influences. It's a bit like a tennis match. The idea gets batted to and fro between the real world and the world of the mathematician's imagination. So I think, but in some ways, it's a very mysterious process. I mean, over my career, I've written more than 200 research papers, often with various people, and these have arisen from almost any kind of inspiration. It's a chatting over coffee at some point with somebody that you haven't actually met before, or there's an obvious problem that everybody knows about, and you think it's about time you should do something about this stupid thing that nobody understands. So the whole history of mathematics is full of problems that knock around for hundreds of years and problems that people think up and solve within the next 10 minutes.
One thing that strikes me in what you said and in all the stories in your book is there's very little discussion of a kind of economic incentive. So meaning you didn't say, oh, we get problems because our dean tells us to, or because we have to get tenure. And I really genuinely believe that's true, right? That most mathematicians seem to just want to work.
I agree with that. I'm sort of that way inclined, certainly mathematically. I didn't write books because I wanted to make lots and lots of money writing books. If I did, I wouldn't want to choose mathematics as a topic, although actually it is quite profitable. People don't understand that there's a much bigger audience for it than anyone thinks. But I think mathematicians mostly are not, they're motivated because they love their maths. They want to solve the problem. They're engaged with the problem. They enjoy doing it. It can be quite soul-destroying at times because you spend weeks and weeks and weeks thinking about something and feel you're getting absolutely nowhere. There's one problem that I worked on for something like 20 years. And after 20 years, I had a kind of 3/4 of a solution. I could solve it with certain extra conditions. It was worth doing. And a few months ago, somebody that I've never met suddenly sent me a paper saying, oh, I've solved the whole thing. And my thought was not, oh, I wasted 20 years of my life on this. I thought, oh, isn't it great? Someone's finally done it. This is wonderful. So I think there's less competition between mathematicians. There's more sort of, you support each other, you get to know each other. And yeah, we're not in it for the money. But there is, of course, for academic mathematicians these days, I'm fortunate I've retired long ago. This doesn't affect me. But the kind of publish or perish attitude is to some extent forced on people by the administrators and grant funders and other such people. So there is pressure now on the current generation of mathematicians that certainly when I started, which was back in 1967, and got the first job, academic job, that sort of pressure wasn't around at all. It's amazing what wasn't around them. We didn't have any computers. The university had one computer for the whole university. We didn't have photocopier. Oh. I mean, we had a lot of fun with all sorts of weird gadgets. Nowadays, it's all been taken over by the computer. You've got a computer and a printer and internet connection, and you can do almost anything. You know, you can produce your own book from start to finish. It wasn't like that. We were scribbling things in multicolored inks on special paper that would duplicate 100 copies of the question sheet for the students and things like that. When IBM bought out the golf ball typewriter where you could switch the golf ball and get mathematical symbols, it was a great advance over the extremely antiquated technology that our secretaries were having to use. It's all much slicker now, but it was a lot more fun when you had a dual keyboard typewriter on the desk with mathematics on one side and the ordinary keys on the other side. And when you wanted to switch to a mathematical symbol, you pushed a button and the entire carriage lifted up, rolled across to the other side, crashed down again. You could always tell when the secretaries were typing a paper because you'd hear bang, 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 say between math symbols and ordinary letters. Yeah, we've lost that. It was more like a cottage industry, I think, in those days.
Now, if we're looking at some of the problems that we're going to solve over time, when problems essentially are born, you say that it comes down to breaking a hard problem in manageable pieces, and then you push through the idea to its extreme. So, as you were writing the book, can you tell us a time that you found one of these problems really interesting?
Yeah, no, they're all interesting, but some are it's like Animal Farm. Some are more interesting than others. I don't work in an area which I found absolutely fascinating, which is mathematically we called it minimal surfaces. The rest of the world would see it as soap bubbles, basically. So you have, for example, you take it. Let's do the real world version. You take a piece of wire, you bend it into some weird shape, you dip it in a tub of soap solution, you lift it out again, and a bubble forms across the wire. And the mathematical question is, given the shape of the wire, what shape will the soap film, the bubble, be? Yeah. And this turns out to be an extraordinarily deep and difficult area. And even the simplest version of this would be you blow a bubble with a children's toy, soap solution and a ring, and you blow through the ring and out comes the bubbles. What shape should they be? And the answer is, well, if they settle down and there's no wind blowing, then it's going to be a sphere. It's going to be perfectly round. Soap bubbles are round. And the physical reason is that that's the way they minimize the energy in surface tension in the soap film, given the amount of air that's inside the bubble. So mathematically, this is minimizing some quantity subject to constraints, the amount of air. But now it's sort of obvious to everybody that the minimum energy corresponds to the minimum surface area. What shape with a given volume has the smallest surface area? It's a sphere. Because if it wasn't a sphere, it would poke out a little bit somewhere, and then if you squash that flat, you could make it rounder without changing the volume. So intuitively, we feel that the sphere is the obvious minimal surface enclosing a given volume. It's extraordinarily hard to prove that that's correct. See, mathematicians like proof. You don't just blow a bubble and say, oh, look, it's round. You say, I want a cast iron proof, no loopholes, nothing missing, that the only surface that has this minimal area is the sphere. In fact, there's an even simpler version of this, which is the two-dimensional version. Which curve on a flat sheet of paper has the shortest length to enclose a given area? It's a circle. Yeah, because again, if the circle was poking out a little bit somewhere, you could kind of flatten it down and grab a bit of extra area without making the curve shorter. Even that's quite difficult to prove. Of course, there's this lovely myth about the founding of the city of Carthage, where Dido, who has been basically thrown out of where she was living and has gone across the Mediterranean to Carthage, and she talks to the king there and says she wants to build a city. And he says, yes, I'll give you some land to build a city, as much land as you can enclose within one ox hide, the skin of one ox. And Dido, being very clever, cuts the skin up into very, very, very thin pieces and makes a huge long string out of them, and then encloses a circle, because that's the biggest area she can build her city in. So The history of that problem goes right back to very ancient times. It's probably a myth, but it's a myth with a serious mathematical message. Then comes through to the sphere version, what shape are bubbles and why are they that shape? Then it gets more general. Yeah, well, instead of having a free-floating bubble, let's have a wire, some wire curve in space. What shape do you get? Can you prove mathematically there is a minimum surface, let alone find out what shape it is? That turns out to be very hard. And in recent years, various people have started to discover that these minimal surfaces can be extraordinarily complicated and beautiful, and they can have lots of holes in them.
Now, Ian, one thing that came to mind in your beautiful discussion there with this ancient Carthage story is when we go back to ancient times, there's a lot of beautiful mythology that inspires or helps explain math, like Zeno's paradox, taking these steps, half the distance, half the distance. There's one about placing grains of rice on a chessboard with exponential growth. But it's making me wonder, those are really human, compelling ways of making mathematics kind of live and breathe and feel relatable and fascinating. Do we still have that today? And if so, where do we get these kind of stories that animate mathematics?
Okay, yes. I mean, I think you put your finger on what I consider to be very important. This is storytelling. Even a high-powered mathematical proof in a journal paper on something very technical is at least an attempt to tell a story, because it's got a beginning. It's the assumptions you make before you start going into your proof. It's got an ending, which is the theorem you want to prove. So Pythagoras' theorem, the sum of the squares on the two sides of a right-angled triangle equals the area of the square on the longest side. Given a right triangle, that's the story starts. The sum of the squares gives you the square on the longest side. That's where the story ends. The proof is the bit in between. Now, those of us who go through Euclid's proof of Pythagoras' theorem find that the bit in between is quite complicated, quite technical. It's not a very compelling story until you get used to that sort of geometry. And then some people find that this is really, really fascinating, this kind of stuff. But it's all a bit old-fashioned. But a good proof, even in a mathematics journal, should tell a clear story, and the person reading it should have some idea of whereabouts they are in the story at the time. It's okay to keep a few things up your sleeve. I mean, a detective story isn't great if they tell you on page 1 who killed the victim and how they did it, although there are some books that do it that way, of course. But your traditional detective novel will, you only find out in the last few pages who done it and how, and it turns out everything's completely different from what you thought it was. Well, you don't want too much of that in a mathematics story, because you want to be able to follow what's going on and have some idea where you're going. But stories are, I think, important. I once wrote a paper for a rather weird conference held in the north of the Arctic Circle in Sweden, in a place called Abisko. And the conference was called The Stories of Science and Science of Stories. And I rewrote the nursery story of the Three Little Pigs, huff and I'll puff and I'll blow your house down, that one, and the Big Bad Wolf, and the House of Straw, the House of Sticks, the House of Bricks. I rewrote that in bad mathematical style to show how not to present a mathematical proof. So it starts with pages and pages of definitely let Pj equal pig, j equals 1, 2, 3, and so on. You see. Yeah, and then I also took a bit of Romeo and Juliet dialogue and rewrote that as a kind of computer program story. And again, it loses all possibility of human interest when you do that. You can check exactly what's going on at every stage, and it's completely boring and no emotional feel to it whatsoever. So, yeah, storytelling is important, but you have to get the right kind of story for the right kind of context.
So, Autumn, one thing I find fascinating with this answer is, as Ian mentioned, storytelling. Here's a man who's written about 40 popular math books. I assumed he was going to talk about writing math for the public and storytelling. And no, he actually went to mathematical research and storytelling there. So I'm curious if you can push him a little further on this point.
Well, in my mind, it's all part of the same thing. I'm not sure my colleagues entirely understood that, but they're very tolerant. And, well, I retired many years ago now anyway, but I still go into the department. I'm still doing research. And my research feeds into my popular math books, and sometimes the popular math books do feed back into the research, because if I'm trying to, in the popular maths books, I'm trying to explain something that I find interesting, but is technically quite difficult and involves a whole lot of knowledge that nobody else has. I mean, mathematicians have this stuff in their heads that nobody else would want to have in there, let alone has in there. But there are plenty of people who are interested in finding out, what are mathematicians up to, what's going on in math. So I have to bridge the gap between the research people and the audience, which is infinitely intelligent and zero knowledge, so to speak, or in practice, not quite that smart, but know quite a bit more. So trying to do that, I get the research stuff clearer in my own mind in order to be able to explain it to somebody who knows less about the background. If I was talking to a mathematician, there's a whole pile of things I could assume, so I don't think about them. Whereas if I'm talking to the ordinary person in the street, so to speak, I have to think a little bit more deeply about how it fits together and what it really means.
And what I found when going through research, no matter what field, whether it's math or in science, you have to be able to tell that story. And I found it funny that you mentioned even the parallels with poetry and writing poetry, because there have been so many interesting stories just in science in general. Is there some sort of example that you have where a pattern may have seemed trivial at first, but then it turned into something that's profound?
Yeah, I can tell you, it's not in the book, but it's in one of my other books, of course. There was a period when I started thinking about the animal movement, the patterns with which animals move their legs. If you watch a dog running or walking, watch a horse, a cat, after a while you realize that there are certain standard patterns that they use, and you can tell when a horse is walking or trotting or galloping. When you look at, for example, the trot of the horse is very interesting, because what happens is that diagonal pairs of legs move. So the front left and the back right move together, and then the front right and the back left move together, and it's equally spaced. So it's like it's standing on two pairs of legs and just moving that way. Whereas if a dog is bounding, as they say, the back legs hit the ground, then the front legs, then the back legs, then the front legs. Now, there are symmetries in this. The dog, it's very simple. If you looked at a dog bounding in a mirror, um, the left and right halves are doing exactly the same thing. So it's symmetric under this left-right reflection. Whereas the trot, if you reflected the horse in a mirror, it would still be trotting, but what was the left leg would become the right leg, and the horse and its image would look different. They'd both be trotting, but they'd be out of step with each other, so to speak. Anyway, this all started when I'd been working with mathematician friends of mine on patterns of periodic oscillations, that is, things that repeat the same movement over and over again, like the horse's legs. Coupled systems. You have several systems and they're hooked up together, and if one of them moves, it affects the others. And we had classified the patterns. We come up with a mathematical theory of the possible patterns in these systems in the abstract. And then New Scientist magazine, which was a popular science magazine in the UK, sent me a book to review, which was by a whole bunch of engineers on taking inspiration from nature. And there was one which was about robots with legs, and they were linking it to the movement of four-legged animals. And they put up some mathematical diagrams, being engineers, of what the patterns were in the legs of the animal. And I looked at these diagrams and thought, they're exactly the same diagrams we were doing in our abstract analysis of these coupled oscillators, as you call them. So when I wrote my book review, I mentioned this at the end and said, can anyone fund an electronic cat? And about 3 or 4 days later, the phone rang, and it was a young American bioengineer. His name is Jim Collins. He is now very famous.
Yep,
Um,
I know exactly who he is.
Jim Collins, yeah. He was doing he was doing various things to do with animal movement and robot movement in those days. He phoned up and said, I can't fund an electronic cat, but I know people who can. Can I come and talk to you? So he came and talked to me, and we never did the electronic cat, but we wrote several papers together on this link between the abstract mathematics and the patterns in the animals. And then various of my colleagues joined in, and from time to time we still churn out another paper on this stuff when we come up with new ideas. I've got a younger colleague at University of Warwick at the moment, and he's very keen on insect gaits, as they're called, the way insects move there. They've got 6 legs. There's more scope for interesting patterns with an insect than there is with a horse. Yeah, so we're looking into insect locomotion. But this began as a completely abstract investigation into a topic that we looked at because it was the natural next step mathematically from something we've been doing. And purely by accident, it became clear that this somehow related to the animal movement, and everyone enjoys animal movement. I can give the same talk to a science fiction convention, a bunch of kids in school, or a whole pile of professional mathematicians at a conference with exactly the same slides on the animal locomotion math, and they all love it.
Autumn opened by asking you about where math problems come from, and we had a nice discussion there. And now you're giving this beautiful example where sometimes nature is the answer. And going through your book, there's so many examples like the six-fold symmetry of snowflakes to movements of planets to neural networks coming from neurons in the brain. So a question that actually just came to my mind now as you were talking is, do you think mathematicians would have found these mathematical systems on their own if it weren't for nature, or we really needed nature to give us these ideas?
I think that we definitely need nature to kick the process off and to equip us with the kind of brains that will ask that kind of question. Yeah, it's this interesting. I mean, the philosophers have great fun with this, and the neuroscientists have fun with this. There's a sense in which everything we do, everything we see, everything we perceive around us is actually happening inside our heads. When I look at a computer screen and see faces and things on it, actually, I mean, there must be a real computer screen and real faces on it to create the image that goes into my eyes, but then the brain processes it, and what I see is actually the result of that processing. It's actually a very interesting mathematical problem as to how the visual system works. But I think, firstly, we take inspiration from nature in all sorts of ways, but once we've internalized it into our heads, particularly as mathematics developed and as human beings got more intelligent and started being, I mean, we ask questions. We're always curious about things. We're nosy. We want to know what's going on. We want to know what the neighbor next door is doing. We want to know what the person down the road is doing. We want to know what that big yellow thing up in the sky that comes out at night and changes shape is doing. It's all part of this sort of human curiosity. But nature inspires a lot of our math, sometimes in ways that I think we might not always recognize the link. One way question is sometimes asked, suppose your environment was very different. When we talk about nature, what we actually mean mostly is the aspects of nature that we experience ourselves. Now, suppose we had alien creatures living on a very, very different planet. There's this idea that the way we would communicate with aliens is we send them 1, 2, 3, 4, 5, and then we send them prime numbers, and then we show them Pythagoras' theorem. And Carl Friedrich Gauss, who was one of the great mathematicians back in the couple hundred years ago, thought the way to communicate with aliens was to draw the diagram for Pythagoras' theorem in the Sahara Desert so they could observe it from space. My
Or
view
crop
is,
circles too?
yeah, oh, quite. Yeah, I mean, you can go in all sorts of directions from this, but the direction I want to go in is that works fine for aliens who are like us, grew up in an environment like us. But suppose they were very, very different. Suppose, for example, I mean, what let's stay on this planet. What sort of mathematics would a fish come up with? Well, fish have this intuitive understanding of the flow of water because they live in it. When you watch a shoal of fish all moving together very, very fast, not bumping into each other, this is, of course, because they are sensing the flow of the water. But to think like a fish must be rather different from the way we would think. We have some sense of the flow, but we don't think about it the way a fish would. So fish-like aliens would probably understand fluid flow far better than we do as human mathematicians, but might have trouble counting 1, 2, 3, 4, 5, particularly if the ones who lived on the bottom of the sea would have pebbles and things to play with, and they could count the pebbles. But the ones that are sort of halfway up in the middle and never really see daylight and other things, numbers would be very puzzling. But turbulent fluid flow, oh, that's easy. That's completely trivial. And for us, it's exactly the other way round.
Absolutely. Thinking about this a little bit differently, as humans, we end up oftentimes pushing for extremes, especially in mathematics. So, a lot of the time you say, and throughout the whole book, is that mathematicians don't just solve problems, they push for them. And you're asking questions like, what's the best possible version of this? What's the tightest bound? And what's the strongest theorem? So why isn't solving a problem enough?
Mathematicians are never satisfied, and it is. I mean, you're absolutely right, and if you look at the history, this is how it goes. So let's take the four-color problem. So there is this. It has been solved within within the last 40 or 50 years or so. It's been solved, but for a long time this problem was hanging around. Take a map and just draw the boundaries of all the countries, so a map of Europe or a map of the United States, all the states, whatever, and you've got some coloured pens, like a kid in school colouring things, and you want to colour it so that you never have two countries next to each other that have the same colour. So you can see where the boundaries are. And quite a while ago now, experimenting with this, a young man discovered he could always do it with four colours. And it's very easy to prove you sometimes need four. You can concoct a map with four regions, each of which has a boundary with the other three. You can put one in the middle and just three round the side, and they all touch each other. So you definitely need four, but nobody could find one that actually needed five. And then there's this long history of people thinking they've proved that four is the best possible, and then somebody else saying, no, there's a mistake, sorry, you got it wrong, but you missed something out. But your proof works for five, and it was known for about 100 years that the correct answer to this problem was either four or five. Now, this is for mathematicians, this is a red rag to a bull. This is, you cannot leave it at that. You can't say, oh, well, it's four or five. Who cares? We don't want to colour maps anyway. It's not a practical problem. And it's not. I mean, nobody's interested in it because of the maps. Mathematicians were interested in it because they couldn't solve it. And because there was this tantalising gap. Four experimentally was all you ever needed. Five you could guarantee was all you ever needed, but you couldn't actually knock the whole thing on the head and say, it really is four. Look, there's this amazing map with 637 different countries, which needs five. Eventually this was solved. It was one of the first examples of computer-aided proofs. So it was solved by Kenneth Appel and Wolfgang Haken. What they discovered was that you could come up with essentially a list of about 2,000 maps, fairly simple ones, 15 or 16 regions. And if you could prove that each one of those maps had a particular mathematical property which was related to being coloured with four colours, but was slightly stronger than that, then you could prove the whole thing. And then you could check this particular property one at a time on the 2,000 maps by getting the computer to do thousands and thousands of calculations for each one of the maps. And at the end of the day, if the computer says, yes, it works, you've proved the theorem. And what happened after that was, what should have happened was, wow, fantastic, they proved the four-colour theorem. For some people, that was the response. But for a lot of them, it was, don't really like that proof. It's massively complicated. No human being can possibly check it. If you wrote it down, it would fill a library. Is that really a proof? Do we trust the computer? And as one mathematician, Robin Wilson, who's a friend of mine, said at the time, the audience divided into two classes. Those under 40, those over 40 didn't trust the computer to get the proof right. Those under 40 wouldn't have trusted human beings to get the proof right and were much happier with the computer proof.
Now, Ian, let me ask a slightly provocative question here. So this was several decades ago. We have this sort of somewhat formal verification of four-color theorem. But as you're saying, a lot of people wanted a conceptual understanding. And as far as I know, we still don't have that. So my question is, do you think getting that computer-aided proof actually discouraged people from seeking out what we really wanted, which is to understand the thing? So did we actually set ourselves back by solving it with a computer?
Okay, you say it's provocative. I don't think it did, but it's because mathematicians are the way they are. There were enough of them who were still saying, instead of saying, oh, the computer solved it, that's great, we can go on to something else. What most mathematicians, even the ones who thought that really was, it's an amazing piece of work. Firstly, it's no longer in any great dispute. As you said, you have proof verification systems now, so you can check that the computer got it right. Yes, you have to use another computer, but it's a kind of bootstrapping system that you write a very simple program that any human being can understand, and then you bootstrap up to very, very complicated things. And at each stage, you have a guarantee that a human can understand of why it's working. Yeah, but there was this residual feeling, quite strong one, that it would be so much nicer if there was a proof that it had some really clever idea that you pluck from thin air somewhere and say, oh, think about it this way, then after a while it's obvious that the answer must be 4. That's what mathematicians wanted. I think what I said in the book was that what they wanted was a poem and what they got was a telephone directory. But this urge to never be satisfied, most people will think this is a stupid thing to say, but what mathematicians want to do is simplify everything. The problem is what mathematicians think is simple doesn't always agree with what the rest of the world thinks is simple. But nonetheless, in our own little way, we're not trying to make it incredibly technical and complicated. It so often ends up that way anyway, but we want to get at the essence of what's going on. And one reason for not just saying, fine, solved it, yeah, you solved the 4-color theorem on a flat piece of paper, a plane, but there are so many other related problems, and we don't want to have to solve all of those the same way with this horrible, massive computer-aided calculation that gives us no insight or very little insight into why it works. If we're going to generalize it, if we're going to ask related questions, similar questions in different contexts, this is another urge that mathematicians always have. I don't think they did in the past, but somewhere about 100 years ago, this became a reflex. Whatever theorem you've got, you want a more general one. You are never satisfied. Yes, I mean, if you solved it for every conceivable topological surface, oh, what about 3-dimensional spaces? What about 4-dimensional spaces? What if they've got boundaries? What if you can just do this thing forever, but different people pick up different aspects of these generalizations, say, oh, that's interesting, and maybe I could do that one. So you want more understanding than just the answer. You don't even want to guarantee the answer is correct, although you certainly need that. You want some insight into why that's the answer, which you hope you can then transfer into other problems, related problems. And this is how mathematics has built itself over the millennia. At any given stage, you solve what you can, but you are constantly pushing out the boundaries, reaching for the extremes. Yeah.
I have a question that follows with this, and it's also going to foreshadow a couple of other episodes that we're going to have after this with mathematics and computer science. And I'll just say, whether it's lean theorem provers or just using AI and technology, are there even real boundaries anymore beyond having these set of rules that we give as definitions?
That's a very good question. I mean, a lot of people, I was talking to somebody on a plane, I was sitting next to someone, we were flying back from Turkey, I think, discussing things, and he said, but surely in mathematics all the problems have been solved, the only things left are the applications. And I said, no, it's the exact opposite. I said, the bigger the area of stuff you have solved, the bigger the boundary at the edge of it where you want to push beyond it and find out what's going on. But I think there is, you're right that in some senses, the boundaries are not as rigid as they were. And there's a tension between AI possibly just taking over and making mathematicians obsolete. It gets so smart that it's smarter than we are. And on the other hand, AI as a new tool, which if used sensibly and intelligently, can solve all sorts of problems for us, including mathematical problems. And there are already examples now of some quite important mathematical problems that have been solved essentially using AI. I mean, you don't just say to the AI, here's the problem, tell me the answer, but you can interact with an AI system. Terry Tao in the States has been doing this. He is one of the best pure mathematicians in the world at the moment. And he is embracing this technology, using it constructively and getting really good mathematics out of it. So, I mean, the solution of the protein folding problem by AlphaFold, it's not a completely rigorous mathematical answer. You know, the question is, given the sequence of amino acids in the protein, which you can get from molecular biology easily now, what shape does it fold up into? Because for the way the protein works in the human body, let's say, it's the shape that matters, not the amino acid sequence. But it's easy to get the sequence. Can you deduce the shape? Well, it's an extraordinarily hard mathematical problem, but AI systems can now solve this very fast with it may not be the perfect shape, but it gets pretty close to the correct answer. very quickly for hundreds of thousands of proteins. This is like having one problem which will take 5 Nobel Prize winners 100 years to solve and doing 100,000 of them in 10 minutes.
I still see this larger issue here where the protein folding is this fascinating mathematical problem, right, of finding the shapes that these sequences end up in. And we've created a tool that can solve it in the sense of giving us an answer, but I don't think it's really brought us any closer to understanding. So
That's
isn't there
right.
something, as a storyteller, don't you feel a little sad that we seem to be marching towards a world where we can solve without understanding? We're kind of
I
taking that out.
do, and it's a repeat of the four-color theorem in the sense that, yeah, you got the answer. Now, at least with the protein folding, it's an answer that people really do want. It's useful. You can do a lot with it. So you can justify the existence of the whole thing very easily with that and just say, look, as a practical matter, this really does solve the problem. Do we need more than this? And certainly the medical practitioners and other people who want to understand this, biologists and so on, would probably say, I don't care how you get the answer, as long as I know it's a good answer, that's what I want. I start from that. But the mathematicians, and to some extent even the computer scientists, will want your point of view on this, which is, yeah, but we haven't really got as much insight into the nature of the problem as we would like. Yes, we can generate answers indefinitely. I mean, imagine if you have a vast arithmetic textbook with 5 million problems in it to solve, and then somebody gives you another book which has the 5 million answers to it in it. What have you gained?
A heavy book.
Yeah.
Heavy book, or one of the lines in Gilbert Strang's linear algebra that says, I'll tell you about it later, and he never tells you about it later.
Yeah.
Cliffhanger. See, we're back to
It's known as
storytelling.
proof by indefinite postponement in the
The new type of proof that we're going to have.
there's various there's proof by personal incredulity. I don't believe that.
One thing
There's
you're
about
making
a
me
dozen or
think of
more of these things.
is
Yes.
it seems plausible that maybe we'll end up in a world where we have to kind of split the word proof to having the things that we know are true and the things that we understand as humans. And that used to coincide for thousands of years. Those were the same. And maybe they're bifurcating.
That is very possible. Yeah, I mean, the whole urge for proof probably goes back to the ancient Greeks. They're the first ones to really seize upon this as something that they considered to be important, not just important, but absolutely central to the mathematical enterprise, and also just the whole logic and rhetoric and things like that. How do you know that a logical argument is correct? Well, that's asking for a proof of a slightly different kind from a mathematical one. But proof meant something that will convince an intelligent human being who knows which questions to ask, knows all the awkward things that might go wrong, something that will
Demonstration
convince,
in French,
yeah,
we
something
call
that
it.
will convince them that in fact it's correct. And yeah, I mean, there's a textbook definition of a mathematical proof, which is a series of logical steps, each of which follows from the previous one. Yes, that's what they look like, except nobody actually writes all the steps down. But then there's the other side of it, which is, oh well, it's a story. It's a story that goes from hypotheses to conclusions in a logical manner. But you have to remember that a proof for mathematicians is a story that has to be believed by mathematicians. You can't just tell a nice story. They want to pick holes in it. It's a natural reflex. As soon as somebody announces they've solved a big problem, everybody else says, how do you know that? You sure you got it right? Let's have a look. What about this? What happens on page 73? I don't understand that. And sometimes it turns out there's a mistake, which is why we do it. But, we are trained to pick very nitpicking logic and pick holes in things and say, but you've forgotten what, what if this particularly strange condition happens? Then what about that? You can't just assume everything in the garden is lovely. It's the nasty weeds and other things that you have to look after as well.
I'm thinking about future generations of mathematicians. We're looking at a world with AI and massive computation right now. If you were advising the younger generation or somebody starting in high school, early days of university, or a brand new professor, how should they choose the problems that they're going to work on?
Okay.
We're pushing for the extreme
Right.
here.
Yeah. Okay. I think you have to choose problems that interest you, actually. I don't think I wouldn't want to advise people on problems that they should work on. My attitude with PhD students has always been they get their PhD when they come and tell me something I haven't told them to do. But my job is to guide them in what might be good directions, fruitful directions, but they've already chosen to work with me and they're already interested in the area that I work in. So they've done their bit to some extent already. They know what they're interested in. But I think you have to develop your own sense of what is worthwhile, what is worth doing. I'm always a bit unhappy about the way in some subject areas, I won't say which ones I'm thinking of, but there is a tendency for certain problems to become fashionable and then everybody in the area wants to work on them. Mathematicians kind of do the opposite. As soon as more than half a dozen people are working on some problem, particularly if they're very good, everyone else says, well, I think I'll leave it up to them because they're going to get there before I do. There'll be the odd one who will say, no, I want to join in, and that's great. Mathematicians tend to spread themselves across different problems. We don't work on something because it's the latest fashionable thing, or if we do, we work on some aspect of the latest fashionable thing that we think nobody else is doing. And maybe to be fair to these other subjects I'm thinking about, they do a bit of that as well. So I think you really need to go with your own instincts. If you're a bright young mathematician, the last thing you want is an 80-year-old to tell you what to do. However, the old dog knows you can't teach the old dog new tricks, but the old dog knows the old tricks pretty well.
And usually has a lot more wisdom
Yes.
than someone coming in.
That's right.
Well, I think that's key because one thing I really got reading your book is since there is a lot of history that's tied to contemporary developments, it's just seeing the cyclical nature, right? We hear about this in the history of wars and countries and things, but in math, just, everything that's new is old. So in a way, someone who's been around for a while, I think, is the best equipped to weather the AI storm. So we appreciate your wisdom, Ian, for sure.
Yes.
Well, it's very kind of you to say so.
Now, if you have any advice for future generations or something that you want listeners to take away from this conversation, what would you want them to know?
I think what I would like the great majority of human beings to know is that mathematics is not a dead subject. It's a very, very live subject. There's more math being created now than at any time in the past. It's more useful than it was at any time in the past. And math in the past had a huge impact on human civilization and development. I mean, just improvements in navigating meant that ships could sail the ocean much more safely and get to their destination, and that was important. And actually, math is relatively cheap to support compared to many other areas of human activity, and the payoff is enormous. About 1/5 of the gross domestic product of the United Kingdom comes from the mathematical sciences. There was a survey done recently.
Whoa. Okay.
About something like about 12%, 12 or 13% of people are employed in mathematical sciences industries, and they contribute close on 20% of GDP. Because this includes things like aviation, computing, supercomputing, banking, all sorts of things. These are all intensely mathematical areas nowadays. And I think most people just aren't aware of this and probably wouldn't believe it anyway. They're all sitting there watching this saying, no, it's not, can't possibly be. But an independent survey by accountancy firm found that the contribution of mathematics is much, much bigger than most people think. So I would like that message to get out. We're doing things, they're important, and they actually contribute a lot to the economy of the world's countries, as well as solving human problems that are important for non-monetary reasons.
Maddox has never been satisfied. It classified symmetry and then found the monster. It measured land and then invented infinity. And maybe that's the real insight. Mathematics isn't a search for answers, it's a search for sharper questions. And this is why I tell you, always stay curious and stay informed of the world around you. Until next time on Breaking Math.